Niethammer from Germany. Her research interests are the kinetics of phase transitions, mathematical aspects of material science, and analysis of multi-scale problems. And she got some awards also. In 2011, she got the Whitehead Prize of the London Mathematical Society. And in 2003, won Mises Prize of the GAMM. GAMM is the Society of Applied Mathematics and Mechanics Germany. So she will give a talk about the scaling in kinetic mean field models for coarsening phenomena. Please.
Thank you very much for the kind introduction. Of course, it's a great pleasure and honor to be here. So in my talk, I will discuss how to use kinetic mean field models to describe universal long-time behavior in coarsening phenomena. And I will concentrate on two fundamental examples from material science that are quite different in nature, as you will see. So the first one is oswald ripening. So what's that? So here you see a picture of an experiment in a nickel-aluminum alloy. So what happens if you have a system of, say, two components that's uniformly mixed at high temperature, but if you cool it below a critical temperature, then phase separation takes place. And what happens is that small nuclei or droplets or particles, as I will call it in the following, of nickel-rich phase, these are the white droplets, are formed. And the background phase is the aluminum-rich phase. And then the system has separated locally everywhere, but then there's still a lot of surface area present, so there's lots of surface energy still in the system. And the late stage of the evolution, that's what we are interested in, is driven by the desire of the system to reduce the surface energy. And the mechanism, which is dominant here, is that mass diffuses from the small particles. These are the ones with relatively high surface energy per volume to the large particles. These are the ones with low surface energy per volume. And in that way, the large particles grow, the smaller ones shrink and disappear. And you see this coarsening of the microstructure. And notice that we're here on a nanometer scale in this picture. So what we're really interested in is understanding the behavior of, say, millions of such droplets. And just to get an idea how the dynamics look like, here's a small movie of it's an experiment in some polymer system, just to get an idea how this looks like. It's a very short movie, but hope you get an idea. So you have these droplets. They essentially do not move in space. The larger ones grow, the smaller ones shrink and disappear, and you have this coarsening structure. Okay, the second example I want to discuss is grain growth in polycrystalline materials. So here you have a metal melt, and if you cool that below the melting temperature, then you get many small crystal seeds. Here some small nuclei of a single crystal, but in random orientation. Then these crystals grow and finally coalesce and form such a network structure. But since these crystals have random orientation, where the two crystals meet, the underlying lattice in general doesn't match. And so this interface between two crystals again carries surface energy. And again, the late stage of the evolution is driven by the desire of the system to reduce this surface energy. And here this happens in a way such that the atoms migrate along the grain boundaries in a way such that the total, okay, here it's really a two-dimensional picture. We will always discuss the two-dimensional picture. So the interfaces are lines. They meet typically in triple junction. So atoms move along these lines in a way such that the total length decreases, and once the grain vanishes, the whole network rearranges itself without destroying the network structure. So again, here you see a little movie. There you see how the dynamics go. Again, the large grains grow, the smaller ones shrink and disappear. And once the grain disappears, there is some change in the neighbor relations of the neighboring grains in order to keep this network intact. So what is the one important issue in both examples actually is that you observe the universal statistically self-similar long-time behavior. So what does that mean? So first of all, it means that the typical length scales in the system, such that droplet size and oswald ripening, grain diameter, and grain growth, they follow after some transient stage they forget about the data and follow in a universal power law in time. So in Ostwald-Ripening, the typical droplet growth proportional to t to the 1/3 if t is the time, in grain growth it's the square root of t. And we are also interested in the growth rate, so this is this prefactor A here. And then second, universal statistical self-similarity means that this is as in Martin Heiler's talk, so if, unfortunately I don't have the corresponding pictures, if you would zoom out of your coarsening system proportional to these length scales, then the statistics of the corresponding pattern remain unchanged. Another way of saying this is the following: if you plot the histogram of particle sizes, so here you plot the histogram in 3 consecutive times, since you have coarsening, so the histogram broadens and flattens, but if you rescale it according to these typical sizes, then the histogram converges to a unique steady state. This is also called a dynamic equilibrium. And this is what we would like to recover in corresponding mathematical models. So from the point of view of application, well, is interested in predicting the coarsening rates and also the shape of the size distribution. But I think it's also of somehow very interesting from a theoretical point of view to understand when, and if so, why we get this universal long-time behavior. So the starting point is always, in both of these examples I'm going to discuss, is a continuum model for the droplets or grain evolution, but on the level of this model you cannot talk about statistical self-similarity. So what can you do? So you could do numerical simulations for a large number of grains, plot the histograms and try to see what they're doing. However, you really need to do the simulations for a long time, for a large number of particles. In particular, you have to start with a huge number of grains because so many disappear over time. And in principle, you have to do it for many realizations. So this is very expensive. So even with nowadays methods, at least not at all easy, let's say that. So our strategy is different. So it's a bit like Boltzmann, considering the Boltzmann equation in gas dynamics. That might be more familiar to most of you. So we want to derive from this starting point model here, we want to derive an evolution equation for the number density. In principle, for these blue, respectively red curves, we want to derive an evolution equation and see whether, for given initial data, the solution converges to a stationary state after rescaling. And as probably most of you know, in order to derive rigorously or at least self-consistently such an equation, you typically need a small parameter in the system. We will see how that comes in one of our examples. So again, today I will discuss the 2 examples I showed you before. But the situation is quite different. In Ostwald-Ripening, at least in a certain regime, there is a quite well-developed theory by now, and I just want to give you an overview of what has happened in the last decade or so. And in the end, I will discuss briefly grain growth. Here the situation is much more complicated, at least from the point of view of these kinetic models, but I will describe briefly a 2-dimensional model for 2D grain growth, but we will also see there are some limitations as well. So let's start with Ostwald-Ripening. And as I already mentioned, we principally need a separation of length scales in the system. We need a small parameter. And here in Ostwald-Ripening, there's a convenient regime that is still relevant in several applications. That is the regime of small volume fraction, also called a dilute regime. So from now on, epsilon is a small parameter that tends to 0, or at least is very small. It's always the volume fraction of the particles. And in the limit as epsilon goes to 0, there is a classical theory I will explain to you by Lifshitz, Losov, and Wagner, but we will see that the theory is not satisfactory in some sense. So we need to take higher order effects into account. Higher order means that this theory is basically the limit as epsilon goes to 0. Higher order means we take epsilon small but finite, and this gives additional effects. And then I will give you an overview of the type of effects that one might take into account, how one can incorporate them in the corresponding models, and then compare the predictions of these different models. Here's just another experimental picture that shows that also the dilute regime is certainly of some interest. Okay, so I said we have as a starting point a well-established continuum model that we do not want to discuss, so this is the truth if you want. So here in Oswald ripening, the model is known in material science as the Malin-Sickwerker free boundary problem, which is as follows. So we have 3 dimensions. You can think of a large cube in 3 dimensions or just particles uniformly distributed in all of R3. We saw in the experimental picture that it's fine to model particles by balls, and so they're characterized by a center xi, but the center doesn't move, and the radius ri that changes in time. So particles can grow, can shrink, and ri can also go to 0. And then we said they interact by diffusion, so they interact by diffusion potential u. And now the equations are as follows. So since diffusion takes place on a much faster time scale than the radii can react, one can also assume that the potential relaxes instantaneously to equilibrium. So at each time t, u satisfies the stationary diffusion equation, so Laplace u equals 0 outside the particle, and on the boundary of the particles, it satisfies what is known as the Gibbs-Thompson law, and that reflects the effect of surface tension. So the potential is large on the boundary of small particles, it's small on the boundary of large particles. So if particles of different sizes, you have a gradient in the potential, and this induces a mass flux from the small to the large particles. And the growth rate of each particle is just given by the average mass flux in the Okay, maybe if you haven't seen that before, it might be not so easy to digest. So you can think of this problem discretized in time as follows. You have as initial data a system of non-overlapping balls. You solve this elliptic boundary value problem, and then you move the radii according to this law, and then you iterate this process. So this is well defined certainly locally, but then you have potential singularities. The first singularity is that a particle shrinks to 0, but that's not really a problem. It shrinks to 0, and then you remove it and continue with the remaining ones. But then there's another singularity, which is more serious, that is even so particles do not move around in space, if you have 2 particles that are large and grow, they might touch each other. So they come close. And then this is not well defined anymore. Okay, this is a simplified version of Malin-Sickwerker that is not valid anymore. But think about it, we are in a dilute regime, so this doesn't happen very often. Let's ignore this, but keep it in mind because it will become important later. So as long as particles don't touch, the evolution is well defined for all times. One can easily check it has the following properties. The surface energy is reduced in time, so the surface energy here is just a portion of the sum of the radii squared, and at the same time the total volume covered by the particles is preserved. And what makes this evolution actually challenging and interesting also, of course, at the same time, it's curvature-driven evolution, but it's non-local because each particle interacts with all the others via the diffusion potential u. And u is governed by the Laplace equation. So the Laplace equation, the fundamental solution in R3, decays like 1 over modulus of x. So we have so it's a slow decay, we have up to only long-range interaction of the particles. And that's what we need to resolve. And okay, so I said there is a classical theory, and so the formal idea of this, so the theory is 2 parts. First, there's a derivation of a model, a derivation of evolution for the number density, and predictions on the long-time behavior. So let's start with the derivation. The formal idea is quite simple. So again, they say, okay, we are in the limit of very small volume fraction, so the size of particles is much smaller than the distance to the nearest neighbors. So they make a mean field ansatz, which in this case means that they assume that one particle, say this particle I, communicates with all the others only via an average potential, which I call infinity at the moment. Yeah, so all these particles outside contribute somehow to infinity, we don't know at the moment how, but this particle sees only this average value. And then you can solve the Malin-Sickwerker problem from the last slide for the single particle with this boundary condition at infinity. And then this gives a simple, and solve it explicitly, it's easy, and you get a simple simple ODE for the particle radius of particle I. And by the ansatz, the rate of change of the radius depends only on the size of the particle itself, and the interaction is represented by U infinity. And now, how is U infinity determined? Well, the thing which we haven't taken into account is volume conservation. So we say, okay, in addition, the sum of the radii cubed is constant in time. We differentiate this with respect to time, plug in this law, rearrange, and get, in fact, that U infinity must be equal to the inverse mean radius in the system. So in the end, we end up with a system, so we have a huge number of particles. Each particle radius obeys this ODE, and they're coupled only through the mean radius. So it's quite simple in principle. Here you see the particle grows if it's larger than the mean, it shrinks if it's smaller than the mean, but the mean size increases in time, so it becomes harder and harder for a particle to survive. Okay, so this in principle you have a huge system of ODEs, so usually if you want to study the long time behavior, you go over to a number density, so that's what Lifshitz and Wagner did as well. So the number density is in principle a measure, so we integrate from R1 to R2 is the number of particles, in a number density, I didn't write this, of particles at time t with radius in this interval. But then we assume it has a smooth density, and then this density, if we assume that all the particles evolve according to this ODE, and that there are no particles of positive size suddenly created out of nowhere, and also that no particles collide, then the system of ODE is equivalent to this transport equation for the number density. Yeah? So the rate of change of the particle radii shows up here as this function here. Okay, so starting from this complicated free boundary problem, we end up with a scalar transport equation for the number density. So this is quite a significant reduction in complexity. It's non-local because it depends on the mean radius, and that makes the analysis somewhat hard. But okay, we are now in the position to talk about self-similar long-time behavior. This would mean on the level of F, we first ask, are there self-similar solutions, which correspond, if you think back of the red curve, it would correspond to a stationary red curve. And given initial data, does the corresponding solution converge to self-similar form or not? And okay, so this was very roughly the formal idea of how to derive this model that we just mentioned. So this derivation can be made rigorous in the sense of homogenization. So it's really the leading order theory, if you want, in the limit as epsilon goes to 0. Okay, so but now what about the self-similar behavior in this LSW model? So here, first you need to check, are there self-similar solutions? Self-similar solutions are special solutions, of this particular scale invariant form. I mentioned already the typical length scales evolve like t to the 1/3. This is reflected here in this rescaling of the argument, and you need to rescale. You need a rescaling factor in front to keep the volume preserved. And then you also here, because it's a non-local quantity, you also have this ansatz for the average radius. And this FA, again, this would correspond to the red curve in the schematic picture I showed you in the beginning. Now the question is, does such an FA and a corresponding A exist? You plug it into the equation, you get an ODE for this capital F, that is easy to solve, and you find that there are physically relevant solutions. There's not only one, there's a whole continuum of solutions, and correspond to this parameter A, which is our growth rate in the interval 0, 4/9, including 4. And all of these profiles, okay, this is not exactly how they look, really just very schematically, they all have compact support, and they can be characterized or distinguished by their behavior at the end of the support. So for each A smaller than 4/9, there is a corresponding power law at the end of the support, so like linear, quadratic, or any power between 0 and infinity. That's how they behave. And the one for A equal 4/9 has the largest support and the corresponding profile is smooth at the end of the support. It goes like some exponential into zero. So now the question is, okay, you have this whole bunch of solutions, is any of them particularly relevant? And here's what Lifshitz, Lozov, and Wagner actually claim. They claim that only the solution corresponding to the largest growth rate, so to 4/9, is stable. Well, okay, if you look at the original papers, the situation is as follows. So Wagner does not even find, he finds only the solution corresponding to 4/9. Lifshitz and Lozov, they find the whole continuum of solutions, but their argument that the 1 for A equal 4/9 is stable uses an argument that goes outside the LSW mean field model. It takes effect into accounts that are not within this model. We'll come back to this later. So the situation was a bit unclear what this stability means. But if it's the only stable solution, then then the consequences would be that you really have a universal shape of the rescale size distribution. One would expect, at least for generic data, the solutions converge to this form, and you have a universal growth rate for the mean radius, which in the following I will denote by brackets R LSW. So this is what the LSW theory predicts for 190 to answer. But then there was already in the 80s, there was a discussion in the material science literature where they said, okay, are the predictions, so let's accept the mean field model, are the predictions on the long time behavior really correct? And it was going back and forth, the argument, it couldn't be resolved. And then there was actually, you find there the question, why can't the mathematicians help us here? This is a purely mathematical question. Here is this model, what happens given initial data, what happens for large times. And then sometime later, this is how the story started for me in a sense, in joint work with Bob Pego, we resolved these questions, but at the same time one should mention there are also other groups who came to similar conclusions. So Carl and Penrose, considered a simpler model, but with similar results if you want. There's a group of Baruch Meersens, they do not do rigorous analysis, but they came up with similar conclusions. And I want to describe the outcome only informally. So the outcome is that the long-time behavior within the LSW model is not at all universal. Any of the self-similar solutions can appear as a long-time limit, and roughly speaking, is that the solution converges for large times to the self-similar solution with power law P. Remember, they can be distinguished by the power law at the end of the support. This happens if and only if the data behave like the power law of power P as well at the end. So as a cartoon of the dynamics, you can think of that what basically happens that you zoom in at the end of the support of your initial data. That's the only thing the dynamics are doing. And in some sense, for PDE person, it's not so surprising because the LSW mean field model is a pure transport equation, so it remembers somehow the details of the initial data forever. But so we can say, as a consequence, within the LSW mean field model, there's no universality. The long-time behavior depends extremely sensitively on the initial data, and more precisely, it depends on the largest particles in the system. Okay, so this is one disadvantage. So in some sense, the mean field model is too degenerate in a sense. But then there's another problem, which is more from the point of view of applications, is that, of course, there were experiments done to compare the predictions of the theory with the experimental results. And in general, the agreement is not very good. The experiments show much larger coarsening rates and much broader size distributions. So the conclusion is that we have this, in some sense, two problems of the LSW theory: no universal long-time behavior, no too small coarsening rates, and so on. So one needs to take, so this is the limit as the volume fraction really goes to zero. One needs to go one step further and takes finite volume effects into account. So we still talk about small volume fraction, but not the limit epsilon to zero. And there is really a large amount of literature, again, in physics and metallurgy. So this is actually a quite old, but still very good overview. And even then, there is a lot of So what you see here are the results from different theories, different experiments. Q is what we call epsilon, the volume fraction. This is the deviation from the LSW growth rate. And they try to predict, so this would be like some square root, they try to predict how the deviation goes if you let epsilon become positive. But you see, I mean, there are quite many different predictions, and there was no clear agreement on what the correction should be. So that was our motivation to investigate this issue with a more rigorous mathematical analysis, if you want. And if we talk about higher order effects, you first have to think about what are the possible effects that have been neglected in the LSW mean field theory that we need to take into account, or might take into account. And really, due to some time restriction, really I just want to give you some ideas here without going into much detail. But there say at least two different mechanisms of quite different nature that might be relevant. And the first one is what I call fluctuations in particle densities due to screening. Okay, so what do I mean by that? Remember, the main assumption in the LSW mean field theory was that one particle sees all the others in the same way. All the other particles contribute in the same way to the mean field that are first equal to infinity that turned out to be the average radius. But this neglects the screening effect. This is the same as in electrostatics and says that one particle is screened from the particles in the neighborhood from the particles further away. And the general belief is that one consequence is the buildup of correlations, and this again would predict larger coarsening rates. What I mean by buildup of correlations, well, the idea is as follows. You look at the system, your system has run for a long time. You look at it, you find a large particle. It is large because it's more likely to be surrounded by smaller than average particles. And because of that, it can also grow faster than predicted by the mean field theory. And similarly, of course, a small particle is more likely to be surrounded by larger ones, and then it shrinks faster than predicted by the mean field theory. And many theories, again, physics, metallurgical literature, try to capture this effect, but as I mentioned before, that the results were quite different, so there's no clear theory here. Then there's another effect of a different nature, as I said, is the what we might call collisions, might be a bit misleading. Lifshitz and Storozov in their original paper already call it encounters. So this is what I mentioned in connection with the Malin-Sepperka problem, that it doesn't happen very often in a small random fraction regime, but particles might become close after a long time. And the two particles that grow, they become close and then might merge, or even if they do not merge, if they're close to each other, they look to the other particles like one big particle of the double volume. And this is the effect that Lifshitz and Storozov took into account and argued that that's why the one particular solution in the mean field model is stable. I come back to that later. Otherwise, strange enough, the effect was not considered much in the literature. You find it in somewhat different type of Ostwald ripening, but it's really a little bit of a different story. Okay, but certainly one should not forget about this possibility. So why have fluctuations been considered much more closely? So the reason, I believe, is the following. So these are possible effects. How should they scale in epsilon in the volume fraction, and how should we take them into account in our model? And to estimate the size of these effects, we make a back-on-the-envelope scaling argument. I just have to introduce some few quantities for that. So your system, you have this system of particles that are uniformly distributed in R3. The parameters are the volume fraction, epsilon is small, a number density, and an average radius. And then, by an analogy to electrostatics, it's in principle well known that the relevant intrinsic length scale is the screening length. So it's indicated here. So this is the particle, the particle I interacts effectively with the particles within the screening radius. And there's a relation to the capacity density. So the screening length scales like 1 over square root of capacity density. So this is just the capacity density in 3 dimensions. okay, with this understanding, you then ask, okay, how many particles are within the screening radius? So they're roughly of the order 1 over square root of epsilon. So there's still many particles, but not infinitely many, as in the mean field limit. This leads to fluctuations in the equation for the particle radius of epsilon to 1/4. And in effect, in the equation for the number density, you would expect would show up like a term of order square root of epsilon. Okay. So what about the encounters, where the fraction of colliding particles can only scale with the volume fraction, if anything. So since epsilon is small, you think epsilon square root epsilon is much larger than epsilon. Okay, let's concentrate on fluctuations and forget about encounters. But we will see that the story that is not so easy. But okay, on first glance you might expect fluctuations are more relevant than encounters. And actually that's what we thought in the beginning as well. But now you will see the outcome is a bit different. But anyway, with this rough understanding of the scaling, the question is now more precisely, how can we really set up a model that takes these effects into account? Then once we have the model, remember the main question is, does the resulting model have now a unique self-similar solution, which then is an attractor for all solutions? And how large is the correction to the mean radius? So this is always, this is one of the basic quantities you want to know. How large is the correction to the coarsening rate? This is what you saw also in this graph of the many experimental and theoretical results before. Okay, now it goes very quickly, but just really want to give you the ideas, as I said. So this is then joined by Fiscu and Velasquez, where we also first concentrated on these screening-induced fluctuations and derived in a self-consistent way from Mann and Sekerka a correction to the LSW mean field model, and this looks like this one here. So for epsilon 0, right, just in case you forgot it, this is just the LSW mean field model. Then you get a correction which scales as expected like square root epsilon, and it's like a diffusion term in the radius value. Don't worry about the details. But so from a first order equation, you have now a second order equation, even though it's a singular perturbation, but second order. So it's not surprising that this equation now has a self-similar solution that has actually infinite support. It's more like a diffusion equation in R. And it has a unique self-similar solution, so that's nice. And you can compute the correction to the average radius, and the correction scales like epsilon to the 1/4. And you can compute the constants by here. So that looks actually quite promising. Yeah? So you have this this model takes screening into account. You go from, instead of having a whole continuum of self-similar solution, there's only one. And you can compute corrections to the mean radius that confirm that the average radius now grows faster, and you can compute the correction. Okay, but then we thought, okay, let's still look at this, how does it compare with the encounters? And here, okay, the disadvantage is that this model is really a bit ad hoc. It cannot be, or I wouldn't know how to derive it, but it certainly makes some sense. It has been suggested already by Lifshitz and Skvortsov. So they want to take the occasional encounter of two particles into account. Yeah, so the particles come close, then they merge, and the volumes are just added. And this they're modeled by a so-called correlation term. I don't want to go into details if you don't know about that. This is just like simpler but similar as in Boltzmann equation. You have a gain and a loss term. You gain a particle of a certain radius if two smaller ones collide, and you lose one if your particle radius R collides with one. And then you can investigate self-similar solutions of this model. Okay, and there's of course the scaling epsilon, it goes like the volume fraction. And so to investigate self-similar solutions of this model, that's not easy. So this is, but one can do it. And we came up with the following result, that there also exists a self-similar solution. It also has infinite support, but it decays quite quickly. But the interesting thing is that how does the correction to the average radius look like? So it scales like 1 over log epsilon squared. So the correction is much larger than in the model that takes the fluctuations into account. And when we saw that, yeah, even so in the equation for f, the correction is epsilon, the correction to the average radius is much larger, it feels like 1 log epsilon squared. And okay, we were first quite surprised, but then if you think about it for a while, there's actually a non-technical explanation for that fact. If you recall what I said about the mean field theory, so I said the long-time behavior is dominated by the largest particles in the system. Now, if you add the effect of fluctuations, then the trajectories of the largest particles are changed a bit, but there are only a few largest particles in the system, so the overall effect is not so dramatic. Here, with the encounters, is completely different because two average-sized particles can collide and form a largest particle. So suddenly there is another large particle in the system. And there are many average-sized particles. This is the reason why there is such a much more dramatic effect in the correction to the coarsening field. So our conclusion is that, okay, let's just conclude on Ostwald-Reitning. So we saw there is the classical mean field theory, but this is not completely satisfactory, so we want to take higher order effects into account. And first, seems fluctuations, we could develop a model for fluctuation, gives a correction to the coarsening rate of order epsilon to the 1/4. But if you compare it with the model that takes encounters into account, it turns out that, that the correction to the coarsening rate is much larger. So this suggests actually that these encounters are possible explanation for the much larger coarsening rate that you observe in some coarsening system. So, okay, of course there's still many open questions, but still I would say that many aspects are quite well understood in Ostwald-Reitning. So let's talk a little bit about brain growth then. And here's the situation is quite different. Why? So here's just a little movie again, so that you recall what we're talking about. Again, let me emphasize it in 2 dimensions now. You will see why this is important. Now, there's already one difference. In Ostwald-Reitning, we could characterize a grain, a droplet by its radius. So the number density has just one variable, r, at the end of time. Here, to characterize such a grain, we need 2 variables, the area A of a grain and the number of edges or neighbors. Yeah, so we have 2 variables. It makes the things already more complicated. One is discrete, one is continuous. Now, okay, remember in Ostwald-Reitning we derived to leading order and ODE for the radius. Now we have to say something here. How does the area of the grain develop in time and what happens to the number of neighbors? And the starting point here is the following model. It's basically the mean curvature flow. But we need an assumption. We need the assumption that all the interfaces carry the same surface energy. So surface energy is constant, which is certainly not realistic in real polycrystalline material. But okay, let's assume that. Then each of the boundaries moves according to the mean curvature flow. And then these boundaries meet in triple junction. We can assume equilibrium of forces. That means that all the triple junctions, they just instantaneously adjust with the grain boundaries, and the angles are always 120 degrees. And as a consequence of this constant surface energy and the fact that we're in 2 dimensions, there is the famous so-called von Neumann-Marlin's law that you get by elementary computation, that the rate of change of the area of a grain is proportional to n minus 6. N is the number of neighbors. So if a grain has more than 6 neighbors, its area grows. If it has less than 6, it shrinks. If it has 6 neighbors, the area remains constant. But of course, this number of neighbors changes sometimes. Somehow in a discontinuous way due to the following events. So there are 2 types of events. The first is grain vanishing. So you can have grains with less than 6 edges vanishing. So the typical case is this one, this 3. So here you have a small grain. It shrinks to a point, and at this instance, all of the neighboring 3 grains lose an edge. In the other case, it's a bit more complicated, but don't worry about it. So we can lose edges, But then there's another event. This is if only a grain an edge vanishes, not a whole grain. So the edge shrinks to a point, then you have for one instance a fourfold vertex, but that's unstable, it splits up immediately. And so at this instance, two grains lose an edge, two other grains gain an edge. So this is a symmetric event in some sense. This is somehow unsymmetric in the sense that you really lose edges. Okay, the question is these events are not described in a deterministic way, so let's see how we can still incorporate them in a kinetic model. So here are our variables we want. Again, we have a number density, but now we have a whole infinite system of number densities, Fn. So Fn of AT is the number density of grains of area A with n neighbors at time t. So in the end, you will get a whole discrete system, infinite system of equations for the Fn. We have transport in the area variable due to von Neumann law. So this looks like that. But then, this is not zero, that would be trivial, but there are some gain and loss terms due to this grain vanishing and edge vanishing events. And then we need to couple it with boundary and initial condition. That's maybe not so important at the moment. The question is, how do we model these gain and loss events? And there was a suggestion by Fradkov, and what he calls the gas approximation, again in some analogy to Boltzmann equation. And he makes a kind of mean field assumption again, and assumes that under the absence of correlations, you can assume that the flux from n to n plus range with n edges to n plus 1 is proportional to n times Fn. And then you plug that in and rearrange, and then you get the following expression that the gain-loss term is something like a discrete Laplacian in n of n times Fn, and a discrete gradient, so this of n times Fn. This corresponds to the grain vanishing events, this corresponds to the edge switching. And there's still a parameter in the system, which is the ratio between two events that you can choose as you want in principle and try to adjust your results for this model if you're comparing this experiment. But if you would only model the gain-loss term by these brackets, then your model is not self-consistent because it wouldn't conserve the total area covered by the grains. That's certainly something you want to have. So you need a prefactor, a non-local function gamma of f, and this gamma needs to be determined such that the total area is preserved. And then you need to work it out, how does gamma look like, and it looks actually quite awful. So this is the resulting model. So you have for n larger, for 2 going to infinity, you have the system of equations. For the Fn, there's transport in the A variable, and Fn interacts with n plus 1 and Fn minus 1 via these terms. And then there's the non-local factor that don't worry about the details, but it depends in some very ugly way in a non-local ugly way on the whole system of solutions. Okay, now what can we do for this system with rigorous analysis? Well, first of all, what is not even clear a priori is it well posed, but we can show that. That means for non-negative initial data, there exists a non-negative solution for all times with certain decay properties, so that's fine. Then you might ask existence of a self-similar solution. If we recall in the LSW model for Oswald-Reitman, this was basically trivial. Here it's not at all trivial, but in the end we managed to do that. But then somehow we didn't get any further. At least at that point we ran a bit out of steam. So we couldn't say anything about uniqueness of the self-similar solution, nor anything about the long-time behavior in general given any initial data. And again, the question is, okay, there is a self-similar solution, and here's a transport term. Transport always remembers the details of the initial data. Here's something like a diffusion, but discrete, and it's also in the n variable. Is this enough to drive the system to a universal long-time state? And, okay, we don't really know, but we did some numerical simulations. And the simulation suggests that, in fact, the self-similar solution is unique and any solution converges, in fact, quite quickly to the self-similar state. But but this is the numerics, and we are still lacking in proof, so this is still an open question. So I just want to briefly show you this model, and I also have to mention the limitations of this model for brain growth. So it relies heavily on the for Neumann-Marlin's law, which is only valid in 2 dimensions, and for constant surface energy. So for 3 dimensions there's something bit related, but not really the same, so it's not clear. So both are really strong assumptions one have to make. So then there's also this assumption by Fredkopf, the absence of correlation. And the question is here, is that really realistic? In the Ostwald-Reibnick, in the dilute regime, this is kind of clear, but here this is not at all clear whether this is a realistic assumption. One can really question that. So I think it's interesting to develop further the mathematical methods for this type of problems, because there are similar looking models in other applications. So closely related are soap froth, but also there are models for cell structures in math biology. So it would be interesting to develop further methods. Okay, so then I can sum up. So we were interested in understanding the universal statistical self-similar behavior in some coarsening systems. We discussed 2 Ostwald-Reibnick and brain growth. The strategy was to derive and analyze kinetic mean field type models. So the main challenges here are, first you need to derive a model from some, what I call a microscopic model. And one of the key questions, in particular that was in brain growth, but it is still not understood, how significant do correlations develop over time or not? We are currently working on this on some simpler 1D model, but this is still, I think, not well understood at all at the moment. And then the other question is the analysis of the long-time behavior. As I indicated also in the problem for brain growth, there's always a competition between transport and some, I call it mixing terms, coming either from the encounters of particles or here from the brain vanishing events and so on. And one needs to resolve which, does the mixing term really dominate in the long run and drive the system to universal states. So we still have to develop better methods to understand this better in general. Okay, thank you very much for your attention.
Any questions or comments? Yeah.
So, you already commented, but so you were saying that this model is not flexible enough to cover anisotropic and surface tension. And not only that, because I mean, in what you were saying, this grain boundary, as you said, this surface tension is driven by the mismatch. So,
yeah.
Can you, instead of having an anisotropic surface tension, having some model that is kind of model defined partition, so that depends on the relative orientation of the 2 grains?
Yeah, we thought about that if you allow, say, a finite number of angles, then you could get, I don't remember details. So you can say something, but then you need to have different angles taken into account. So you have additional variables that look quite complicated. It wasn't clear whether you get really a treatable model, but in principle one needs to do that. But still you can only allow for a discrete set of angles and not a whole continuum. Yeah, unfortunately, don't know how to deal with that.
Okay. Any other questions or comments? Okay, now finish all invited sessions. Okay, thank you very much.